Most families jump straight into citizen science and waste weeks collecting data that never gets used. Why? Because they skipped the setup. Real research doesn't start with observation, it starts with calibration, protocols, and backup systems that protect data integrity from day one. My name is Lakshmi Venkataraman, and I've spent years helping families bridge the gap between kitchen table experiments and genuine scientific contribution. You're listening to the STEM Lab podcast. Quick note before we dive in. Everything you're about to hear, all the research, the data, the script itself, that's 100% human written and verified by actual educators and specialists. The voice you're hearing, though, that's AI generated. Just wanted to be upfront about that from the start. Now, if you've been with us for a while, thank you. Genuinely. I know there are a million podcasts you could be listening to, and the fact that you keep coming back here means something. And if you're new, welcome. You've landed in a space where we talk about real, substantive science education for kids. Not crafts disguised as experiments, but actual research-grade work families can do together. New episodes drop every Monday, Wednesday, and Friday, so you'll always have something fresh to dig into. Let's jump into today's topic. You're ready to move beyond canned experiments and contribute to actual research. That's the power of citizen science. Your child can collect data that professional scientists actually use, building authentic research skills while addressing real-world questions. This complete setup checklist walks you through everything you need before you head into the field, from selecting sensors that match your child's skill level to establishing data protocols that mirror university research standards. I've designed this guide for families with learners ages 8 through 16 who are ready to scaffold scientific investigation beyond the kitchen table. Now, let's talk about essential equipment and hardware. Before you commit to any project, you need to understand what constitutes genuine research-grade equipment versus educational approximations. The distinction matters. If you're contributing data to platforms like iNaturalist or SciStarter, your measurements need to meet minimum accuracy thresholds. First up is a digital data collection device with GPS capability and camera. Most smartphone or tablet devices running iOS 14 or higher or Android 11 and up will suffice for observational projects like wildlife monitoring, phenology tracking, or pollution mapping. The camera needs at minimum 12 megapixel resolution for species identification uploads and GPS accuracy within 10 meters for location tagging. If your project involves environmental sensor kits, you'll need Bluetooth 4.0 or better for sensor pairing. This is where I see families stumble. They assume any device works, but outdated tablets lacking GPS completely derail georeferenced data collection. Next, you need environmental sensors matched to your research question and calibrated to known standards. For air quality monitoring, specialized sensor kits provide particulate readings that align with EPA measurement protocols, though you'll need to cross-reference against a known good sensor every 30 days. Check the show notes for a link to the current price. Water quality projects require pH probes, dissolved oxygen sensors, and turbidity meters. Budget sensors often drift 15 to 20% from calibration within weeks without proper storage protocols, which corrupts your entire data set. You'll also want a weather-resistant field journal or waterproof digital note-taking system. I've watched hundreds of sixth graders struggle with this exact misconception. They think data collection happens in clean, controlled environments. Real field work means mud, rain, wind, and unexpected delays. Physical field notebooks need synthetic paper that won't disintegrate when wet. Digital note-takers must have offline capability. Cloud-dependent apps fail spectacularly when you're monitoring stream health in areas without cell coverage. Your system needs timestamp functionality and photo integration for complete observation records. Don't overlook your power solution for multi-hour field sessions. Most environmental sensor kits drain battery faster than families anticipate. The Microbit runs approximately 4 to 6 hours on two AAA batteries under continuous sensor polling, while Raspberry Pi-based systems require USB power banks rated at minimum 10,000 milliamp hours for day-long monitoring sessions. Solar charging panels work theoretically, but introduce variables like cloud cover and panel orientation that complicate data interpretation for novice researchers. Budget 1.5 times the manufacturer's stated runtime for realistic field deployment. Sample collection and storage containers matter more than you'd think. Water quality projects require sterile sample bottles, clearly labeled with collection time, location coordinates, and environmental conditions. Soil sampling needs clean trowels and sealable bags that prevent cross-contamination. The universal rule is this: if your sampling protocol can't maintain sample integrity from collection to analysis, your data becomes scientifically worthless. Safety equipment specific to your field environment goes beyond basic first aid, though you absolutely need that. Urban air quality monitoring requires high visibility vests when working near traffic. Aquatic sampling demands life jackets for anyone working within 3 meters of water edges, regardless of swimming ability. Invasive species surveys may require protective gloves and eye protection. Here's something most people miss. You need a data backup system that functions independently of internet connectivity. Cloud storage fails when you need it most. Your backup protocol should include local storage on the collection device, plus physical transfer to a secondary device like a laptop or external drive within 24 hours of collection. I recommend the 3-2-1 backup rule. 3 copies of data on 2 different media types with 1 copy stored off-site. This sounds excessive until you lose 3 weeks of bird migration counts to a dropped tablet. Finally, every sensor drifts. Your setup must include measurement standards and calibration references, pH buffer solutions for water testing, certified reference filters for particulate sensors, color standards for visual observations. Professional labs calibrate daily. Student projects should verify weekly minimum. Moving on to software and digital infrastructure, the technical side separates casual observers from contributors who generate genuinely useful data. You're building a data pipeline that transforms raw observations into research-grade records. Start with a platform-specific data submission app with offline caching capability. Projects like eBird, iNaturalist, and CocoRoz each maintain dedicated mobile apps with specific data field requirements. Download and test the app at home, not in the field. Verify that it caches observations when offline. Some apps silently discard data collected without connectivity. The app should timestamp observations automatically using device GPS time, not user-entered time, to ensure chronological accuracy across multiple observers. You'll need sensor interface software compatible with your operating system and hardware. Arduino-based sensor kits require Arduino IDE version 2.0 or newer. It's free and runs on Windows 10 and up, Mac OS 11 and higher, Linux, and Chromebook via Linux Container. Raspberry Pi projects need Raspberry Pi OS with Python 3.9 or later and relevant sensor libraries pre-installed. Installation eats 2 to 4 hours on first setup, troubleshooting driver conflicts and dependency errors. Block this time before your first planned field session. For local data management, you need a spreadsheet or database application. Google Sheets works for simple observational data, but fails at sensor data volumes. Continuous air quality monitoring generates over 1,400 data points daily if you're logging per-minute readings. Microsoft Excel or LibreOffice Calc handle larger data sets, but require structured data entry protocols. Your software needs basic statistical functions like mean, median, and standard deviation, plus graphing capability for preliminary analysis. I've seen students discover fascinating patterns simply by plotting their first week of temperature readings against time of day. Photo management and metadata editing tools are critical. Research-grade image submissions require embedded EXIF data, date, time, GPS coordinates, camera settings. Most smartphones capture this automatically, but editing apps often strip metadata on save. Use tools that preserve or add metadata. Your workflow should verify GPS coordinates, correct timestamps if device time was wrong, and add observation notes to description fields. Scientific integrity requires documenting every data modification. At minimum, maintain a change log noting date, specific changes made, and reason for change. Something like corrected GPS coordinates for observations 34 through 41, device location services disabled during collection, documents the problem and solution. As students progress, introduce them to proper version control concepts that prepare them for university research methods. For statistical analysis, elementary-age students can generate meaningful insights using built-in spreadsheet functions. Middle schoolers ready for more sophisticated analysis should explore platforms like CODAP, that's Common Online Data Analysis Platform, free and browser-based, designed for K through 12 learners, or R through RStudio Cloud, which has a steeper learning curve but introduces industry-standard tools. Most citizen science projects maintain forums, Slack channels, or email lists where contributors ask questions, share unexpected findings, and coordinate collection efforts. These communication platforms provide the pedagogical scaffolding that transforms isolated data collection into genuine collaborative science. When your child reports a surprising bird sighting and a professional ornithologist responds with context about shifting migration patterns, that interaction builds understanding around how real science communities function. Let's dig into research protocols and documentation. This is what distinguishes genuine research from random observation. Without consistent protocols, you're generating noise instead of data. Every legitimate citizen science project publishes detailed collection standards, exactly when to observe, what to measure, how to record observations, what environmental conditions to note. Download this protocol document, print it on waterproof paper, and bring it to every field session. I've watched students make systematic errors for weeks because they misremembered a protocol detail. The physical document prevents drift from established methodology. Your standardized observation schedule controls for temporal variables. If you're monitoring bird activity, observing randomly whenever convenient introduces massive bias. Weekday morning counts differ dramatically from weekend afternoon counts due to human activity patterns, weather cycles, and species behavior. Your protocol must specify observation frequency, time of day, session duration, and weather conditions that trigger session cancellation. This consistency allows meaningful comparison across time and between observers. Get clear species identification resources matched to your geographic region. Generic field guides frustrate beginning naturalists because they include hundreds of species you'll never encounter locally. Regional guides narrow possibilities. If you're monitoring butterflies in Texas Hill Country, the Texas Butterfly Identification Guide, either physical or app-based, eliminates 90% of North American species from consideration. Cross-reference uncertain identifications using multiple sources, photo field guides, dichotomous keys, and community verification through platforms like iNaturalist's Computer Vision plus Expert Confirmation System. Professional researchers never trust raw data. Your quality control checklist should verify GPS coordinates fall within expected geographic boundaries, timestamps follow chronological sequence, measurement values fall within physically possible ranges like pH between 0 and 14 or temperatures appropriate to local climate, required fields are populated, and photo evidence supports written observations. This systematic review catches errors while memory is fresh and corrections are still possible. Scientific replicability requires that other researchers can return to your exact study location. Document your site with GPS coordinates accurate to at least 5 decimal places, written description of access route from nearest landmark, photos from multiple angles showing key environmental features, notes on seasonal accessibility like whether flooding closes access roads, and potential safety hazards. Update this documentation if site conditions change substantially. Temperature, precipitation, cloud cover, and wind speed profoundly affect organism behavior and sensor accuracy. Your weather and environmental condition log should record conditions at session start, hourly during extended sessions, and at session end. Many citizen science apps prompt for this data automatically, but manual logs provide backup when technology fails. I teach students to use NOAA weather observation standards. It's the same system airport weather stations use, preparing them for how meteorological data actually gets recorded professionally. Sensors fail at the worst possible times. Your field kit needs quick reference troubleshooting for common problems. Sensor won't connect via Bluetooth? Power cycle both devices, verify battery levels, check distance. Readings seem wildly inaccurate? Check calibration date, verify sensor positioned correctly, look for environmental interference. App crashes on data entry? Verify sufficient device storage, check for pending app updates. Document solutions as you discover them. Your troubleshooting guide becomes a living document that improves with each field session. Now let's talk about learning scaffolds and skill development support. The educational infrastructure behind your setup determines whether students develop genuine research competencies or just follow instructions mechanically. This is where pedagogical design matters enormously. You can't monitor water quality meaningfully without understanding dissolved oxygen, pH, turbidity, and their relationships to aquatic ecosystem health. Front-load 3 to 5 hours of structured learning covering the scientific concepts underlying your chosen project. Background content builds the necessary scientific understanding before data collection begins. Blank notebooks overwhelm novice observers trying to remember what data to capture. Pre-formatted visual data recording templates, either printed sheets or digital forms, scaffold the observation process by prompting for required fields: date, time, location, weather conditions, species observed, quantity, behavior, confidence level, and identification. As students internalize the protocol, gradually remove scaffolding, transitioning to more open-ended recording methods. Before submitting data to the official project platform, students should present observations to family members or learning group peers for feedback. This peer review process mirrors how actual research undergoes review before publication. The review focuses on completeness. Did you document everything required? Consistency, do your observations make sense together? And quality, are your photos clear enough for species verification? Middle schoolers can engage with substantive critique. Elementary students need more structured feedback frameworks. Citizen science projects often span weeks or months before patterns emerge. Visual progress tracking maintains engagement during the inevitable data collection doldrums. Simple systems work: graph paper showing total observations by week, maps with pins marking each collection site, running species lists that grow over time. When students see their dataset growing, they develop persistence, a research skill as important as measurement accuracy. After each field session, structured reflection prompts help students think about their thinking. What went smoothly today? What challenged you? What would you do differently next time? Did anything surprise you? What questions does today's data raise? These prompts transform data collection from a procedural checklist into genuine scientific inquiry, the kind that builds habits of mind transferable far beyond this specific project. Make explicit how this citizen science work mirrors professional practice. Point out when your child uses the same sensor as university researchers, follows the same observation protocols as government agencies, or contributes to data sets that inform published studies. Connection to professional research methods and career pathways matters. Show them how student contributions connect to the broader research enterprise and which aspects of this work develop skills used in actual STEM careers. Your initial project should fit within your child's current skill zone while pointing toward natural extensions. A student monitoring local bird diversity might expand to tracking migration timing year over year, comparing observations across multiple sites, or correlating bird activity with weather patterns. Different platforms support increasingly sophisticated investigation as capabilities grow. Before each field session, run through this condensed final check to catch missing elements while you can still address them. For equipment, data collection device charged and GPS enabled, sensors calibrated within required time frame, field journal and writing implements, backup power supply, sample containers and collection tools, safety equipment appropriate to environment, measurement standards for field calibration. For digital systems, data submission app updated and tested offline, sensor software confirmed compatible and running, data backup system ready, photo storage with adequate capacity, weather app for condition documentation. For protocols, project protocol document accessible, observation schedule confirmed, identification resources for expected species, data quality control checklist printed, site documentation current, weather log template ready. For learning support, background content reviewed, data recording templates prepared, reflection prompts available, previous session notes reviewed for lessons learned. Let's address some frequently asked questions. What age can children meaningfully contribute to citizen science projects? Children as young as 8 can participate effectively in observational projects with appropriate scaffolding, species identification, phenology monitoring, and basic environmental observation build foundational skills in systematic observation and data recording. By ages 10 to 12, students can handle sensor-based data collection using platforms like Arduino or Microbit, managing calibration protocols and data quality verification independently with periodic adult oversight. The determining factor isn't chronological age, but rather the student's ability to follow multi-step protocols consistently, recognize when data looks questionable, and maintain observation schedules across weeks or months. Strong reading comprehension and basic arithmetic are prerequisite skills, and the student needs sufficient executive function development to manage the procedural aspects without constant reminders, typically emerging around age 9 to 10 for most learners. How much time commitment does a citizen science project actually require? Observational projects like bird counts or phenology monitoring typically require 15 to 30 minutes per observation session, with frequency ranging from daily to weekly depending on project protocols. Over a month, expect 4 to 10 hours of active field time, plus 2 to 4 hours for data entry and quality control. Sensor-based environmental monitoring involves longer individual sessions, 1 to 3 hours for site setup, calibration, and data collection, but often less frequent deployment, weekly or bi-weekly monitoring totaling 8 to 15 hours monthly, including analysis time. The invisible time cost that catches families off guard is the front-end learning investment. Expect 5 to 10 hours of background study, software setup, sensor calibration, and protocol mastery before your first genuine data collection session produces research-quality results. Projects requiring specialized travel to monitoring sites add transportation time that can double your total commitment, while at-home or neighborhood-based projects minimize this overhead. Do citizen science projects actually contribute to real research, or are they primarily educational? Legitimate citizen science platforms publish data contribution standards specifically because professional researchers actively use submitted observations in peer-reviewed studies, policy decisions, and long-term monitoring programs. For example, eBird data has contributed to over 500 scientific publications studying bird migration patterns, habitat use, and population dynamics, while iNaturalist observations have led to new species discoveries and inform conservation assessments by organizations like the International Union for Conservation of Nature. Projects involving environmental monitoring, air quality, water quality, noise pollution, often feed directly into regulatory agency databases and community health studies, particularly when sensors meet specified accuracy thresholds and data undergoes verification protocols. The educational value runs parallel to, not instead of, the research contribution. Students develop authentic scientific skills precisely because the work matters beyond the classroom, creating intrinsic motivation that artificial science projects can't replicate. However, data quality matters enormously. Observations that don't follow established protocols, lack proper documentation, or fail verification checks get filtered out of research data sets, which is why the setup checklist approach emphasizes methodological rigor from the start. Setting up your first citizen science project properly takes longer than jumping straight into data collection, but this front-end investment determines whether your child develops genuine research skills or just goes through the motions. The checklist approach I've outlined here mirrors how I prepare my own middle school students for authentic scientific investigation: systematic equipment preparation, rigorous protocol adherence, and continuous reflection on methodology. The beautiful pedagogical feature of citizen science is that it eliminates the artificial ceiling of classroom experiments. Your child isn't discovering something already discovered thousands of times. They're contributing novel observations to data sets that scientists actually need. That shift from pretend to genuine research changes everything about student engagement and persistence. Start with a single, well-chosen project, master the protocols thoroughly, and let data patterns reveal next questions naturally. The research skills you're building, systematic observation, quality control thinking, data integrity, collaborative contribution, transfer directly to university research methods and professional STEM practice. You're not preparing your child for science, you're letting them do science right now in ways that matter. That wraps up this episode of the STEM Lab podcast. Thanks for listening all the way through. New episodes come out every Monday, Wednesday, and Friday, so you're never waiting long for the next one. If this episode was useful to you, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It sounds like a small thing, but it actually makes a huge difference. It's how other parents and educators who are looking for this exact kind of content find the show. And if you haven't already, hit subscribe or follow so you get a notification the second a new episode goes live. I'll see you next time.